Welcome everyone to our virtual lesson on 12.4. Before I get into the math for today, I thought I'd introduce to you my recording buddy for the day. This is Smog. He was found outside all by himself. And so for a long time, he actually would hiss whenever you would approach him. And so he's like a dragon. And so, yeah, he got the nickname Smog. And anyway, so if you hear any noises and stuff like this in the background, I apologize, but that's Smog. He cries out very, very loud if someone's not with him, and so he's going to be in the same room, just so hopefully he's a bit quieter. Anyway, so with that out of the way, let's do some math.
All right, so in 10.4, we're going to be talking about polar arc length and nice-ish areas. So the way that we're going to continue 10.4 when we return from break on Monday is that we're going to do less nice-ish areas. So we're going to expand on that. But let's first talk about polar arc length. And so we need to go back. If you haven't already watched the 10.4 pre-class videos, I definitely recommend that you do that because there's well, first of all, I mean, you get all of the theorems and definitions and things that we need for this section, but then also you see a few examples before you get into these in-class examples. So the very first thing that we need is this theorem right here, 10.4.7, for the length of a curve given in polar form. So if we have some r, which is dependent on theta, then we can figure out the arc length of the curve by integrating from a to b. And again, there's a square root. There's lots of things squared, but in this case, right, it's the radius squared and the derivative of the radius squared. Sum those together, throw those in their square root, and that's what we integrate. So let's go ahead back to our example here. We'd like to find the length of the curve given by r equals a on the interval from 0 to 2 pi. All right, r equals a. So this is a bit strange here, but we can go ahead and graph it. And we just have to realize that a is supposed to be a constant here. So if we go ahead, I've pulled up a Desmos graph here. So r equals a, and if a is equal to 1, this is a circle of radius 1. And if r is equal to something else, so in this case 3.1, it's just going to be a circle of radius 3.1. So it's a circle centered at the origin with a specified radius, some constant a. We don't exactly know what a is, but it's just supposed to be some constant. All right, so with that being said, I mean, we could actually guess this one without actually using any calculus or whatnot, just because we know the circumference and therefore the length of a circle. But let's actually get some practice using our definition and everything. And so I'm going to go ahead and say that L, so this arc length, is going to be the integral from 0 to 2 pi. And we're integrating the square root of, and now we need r squared. So in this case, r is equal to a. And so there we go, r squared. And then we need to add that to the derivative of r with respect to theta squared. So the derivative of r with respect to theta. Well, looking at this, this is constant with respect to theta. There is no thetas. And so if you were to take the derivative of this, very similar if you were to take the derivative of y equals 5 with respect to x, the answer is just 0, right? Because in this case, there are no x's. In here, we have no thetas. And so it's just constant with respect to theta. And so we get 0. Now we're supposed to integrate that with respect to theta here. And so, okay, we have the integral from 0 to 2 pi. Let's see, well, a squared plus 0 squared is just going to be a squared inside of a square root there. This is going to be the absolute value of a. I guess there's nothing here that says that a has to be positive. Remember, with polar coordinates, we do allow for negative radiuses, and we do make sense of that. And so now we can integrate that with respect to theta. So we get the absolute value of a times theta. And this is what we're supposed to evaluate from 0 to 2 pi. And so if we plug in 0, we get out 0. And if we plug in 2 pi, well, we get 2 pi times the absolute value of a. And if you remember, right, the circumference equation for a circle is supposed to be pi times the diameter. That's a horrible pi. Let me try that again. Pi times the diameter, or another way to write that is pi times twice the radius. And so if your radius is a in this case, you can see kind of these are matching up very, very nicely, right? So if our radius is a, well, in this case, right, in order to make sure that's positive, we should talk about the absolute value of a, right? Okay, this is making a lot of sense here. All right, so this is a relatively nice example, just getting us used to that theorem and how to use it and everything. Let's do a more difficult one. So I'd like to find the length of the curve given by r equals e to the theta from 0 to 2 pi. And so I've given a kind of sketch of what this actually looks like. And so you see that we get kind of a spiral, and as we go around, of course, the radius is getting bigger and bigger and bigger. And so, okay, that's our picture. And kind of for all of these, I would recommend, actually pausing the video and trying them on your own as if we were in class. This is an excellent kind of level of difficulty for a problem. It's not too easy, not too hard. So yeah, please pause the video, try this one, and then when you're ready, we'll go ahead and go over it. All right, so this is how far I've made it. I wrote down, right, that r was equal to e to the theta. I also took the derivative of r with respect to theta, but when you take the derivative of e, you just get itself. Now I go ahead and I use the formula for arc length, in this case r squared plus the derivative of r with respect to theta squared. And so we can simplify this down, and we have two of these quantities, right? 2 e to the thetas squared. And so now we can simplify with the square root, and we're going to have the integral from 0 to pi. The square root of 2 is just the square root of 2, and the square root of e to the theta squared is just e to the theta. This right here, we're supposed to be integrating with respect to theta, and so the square root of 2 is just a constant. It's along for the ride. And when you integrate or take the antiderivative of e to the theta, just like when we used to do e to the x and stuff like this, right, you just get itself. This is what we're supposed to evaluate from 0 to 2 pi. And so if I plug in 2 pi into this, let's see, we get e to the 2 pi. And if I plug in 0, well, surprisingly, right, you don't get 0, right? Anything raised to the 0 power is 1. And so this is supposed to be the square root of 2 times 1. And so my final answer here is going to be the square root of 2 times e to the 2 pi minus the square root of 2. I don't know about you, but it's nice for some of these to actually be able to check our work, especially, right, we're not in this quiz or exam setting yet. And when I see this picture here, I see that we start off at the origin, more or less, and we go out here like past 500. And of course, we don't do a straight line or anything like this. It kind of swirls around and everything. But I know that my answer should be at least 500, probably significantly more because of how much we actually go down and all this sort of stuff. And so it's nice to double check. I've went ahead and I plotted this in Desmos, and I put down our answer, right? The square root of 2 times e to the 2 pi minus the square root of 2, and you can see that our answer ends up being 755 and change, almost 756. And so we can see that actually this seems like a fairly reasonable answer, right? We should get a number certainly more than 500, but also, right, I haven't taken into account, right, we've almost dipped like almost 200 down or so here. And so, yeah, like 750 and change makes a lot of sense. So, okay, I'm happy with that answer. Let's go ahead and move on. Here's something that's getting considerably more difficult. It's going to be our last arc length problem for today. Find the arc length for the arc from 0 to 2 pi, so I've kept it kind of boring for us. We're always going from 0 to 2 pi, of the cardioid. And the cardioid's equation is given by r equals 2 minus 2 cosine theta. And so again, like last time, I think it'd be a really good idea if you pause the video, try to get as far as you can, at least try to do the setup and everything like this, and maybe expand all of the squaring bits and everything like this. Try to get as far as you can, and then we'll come back and we'll do the rest of the problem together. All right, so this is how far I've made it. I went ahead and I wrote down the r, which is given to us up here. I took the derivative of r with respect to theta. So the derivative of 2 is just 0, and the derivative of negative 2 cosine of theta, well, the derivative of cosine would be negative sine, and so that's why we get positive 2 sine theta here. I go ahead and I plug this into my arc length equation. So I have my r squared and my dr d theta squared. Add those together, take the square root. And so from here, I need to simplify a little bit. I expand out with the foiling here, right? The first, the inners, the outers, and the lasts. And we get this down here. And then I notice that we have a 4 cosine squared theta, and we have a 4 sine squared theta. And so if you factor out that 4, you're going to get cosine squared plus sine squared, and that's just 1. So in this case, it's going to be 4 times 1. So that's just going to be 4. I've combined it with the other 4 up front here. and that's given me the 8. And then I also have this minus 8 cosine theta. So I hope that everyone got to about this spot, maybe a little bit farther. Have another kitten who's attacking us. Here, let me go ahead and pause, and I'll turn around the video and I'll show you this other kitten really quick.
This right here is Little Fluff. I always tell him that he's going to have a really hard time getting adopted, which is, of course, a lie. But he's just very playful, and he thought that, oh, I'll just dance on your keyboard a little bit. But he does not want to be held right now. So anyway, he goes, this is Little Fluff. By the way, my feet are just littered. Here's, yeah, another one. This one's name's Little TJ. Here we have Boots. So, yep, that's my situation, which certainly not the worst that it could be. Anyway, math.
All right, so yes, back to the math. At this point, right, I by all means hope that you made it past this, but this is where we need a trick, right? I think that in order to still simplify the square root and everything is maybe non-trivial here. And so the trick that I want to use, and there's kind of some different ways that you can look at this, but I want to use kind of this idea that we had back from the power reduction rules that we brought up well, in chapter 7 and a little bit before that, maybe in chapter 6 and stuff like this. But you notice that sine squared u, right, when we wanted to integrate sine squared, we transformed this into 1 minus cosine of 2u divided by 2. And so actually, I'd like to go the other way here, right? I want a nice perfect square. And we may notice that this is fairly close. Let's go ahead and do a bit of a rewrite here to try to get it to look like this form here. And so I want to go ahead and maybe factor out an 8. So if I factor out an 8, here we go. I'm going to have 1 minus cosine of theta. And then if I really want it to be in this form, let's divide this by 2. And of course, if I divide it by 2, I should probably also multiply by 2. So let's change this 8 to a 16. And this is what I want to take the square root of. And now in order to make this formula all work out, this means that u should be theta divided by 2, right? Because I just have cosine of theta. And so 2 times theta divided by 2, okay, that would be theta. Good. So let's go ahead and try this. And so let's see. Well, the square root of 16 is just 4. And then I can go ahead and trade all of this stuff in for sine squared of u. And remember, u was supposed to be theta divided by, thank you, cat, theta divided by 2. There we go. And this is integrating with respect to theta. All right, so with that, we can go ahead and now take the square root. And so we're going to have 4 sine of theta divided by 2 d theta. Now we can go ahead and integrate this. And so let's see, 4 is constant, it's along for the ride. The integral of sine should be negative cosine. And let's see, we probably need something else, right? If I was to take the derivative of this, I wouldn't get exactly where I started. I think we maybe need another 2 here, right? Because the chain rule. So yes, that should work out. And again, we're integrating from 0 to 2 pi. And just as an FYI, I swept some of the complications, I guess, under the rug to some extent. Really, this should be the absolute value of sine of theta divided by 2. However, on the interval from 0 to 2 pi, for sine of theta divided by 2, sine is always positive. And so these absolute values aren't really doing anything. And so that's why it's okay to kind of just drop these. So let's go ahead and plug these things in. We get negative 8. And if I plug in 2 pi into theta here, I'm going to have cosine of pi. And if I plug in 0, I'm going to have cosine of 0. And so let's see, negative 8 and cosine of pi is going to be negative 1 minus cosine of 0 is going to be 1. And so let's see, I get negative 8 times negative 2. So that's going to be a nice positive 16 after all is said and done. So the final answer here is 16. Again, that is the length of the curve, that is this cardioid, 2 minus 2 cosine theta, all the way around, right? Once around. I guess I knew it was going to be at least 8, right, from this picture here, because we have to go all the way to this point -4, 0, and then back again. But of course, we take a much roundabouter way, right, to get there. So yeah, I knew it was going to be at least 8, but it turns out the correct answer is 16. All right, and with that, we are kind of all done with the problems that I wanted to do for arc length in polar coordinates. Now let's go ahead and move on to some area problems that are, again, relatively nice. We'll deal with harder problems in class on Monday, but here are some nice-ish area problems that we can deal with. So in this problem here, well, first of all, instead of actually spending all the time and graphing out this limosone, I just made a Desmos graph, and so I'd like to maybe stare at this for a little bit and see what this curve actually looks like. And then I'd like to find the area of the region lying inside of the inner loop. And so we need to go back to our videos and make sure that we have down the equation in order to find the area for a polar equation. So going back to our video notes here, on the very first page, we bring up the theorem that we're going to need, and that is the area, if we have a polar equation, is given by integrating 1/2 times whatever our radius equation is squared with respect to theta on some interval, right, from A to B. And so let's go ahead and maybe write this down since we're definitely going to need that. So again, the integral from A to B, 1/2, oops, that's a horrible 2 down there. There we are, 1/2 and the radius squared, integrating that with respect to theta. And so, well, already we could set up the integral from A to B. I could do the 1/2, and I could write down, right, we know my radius equation here is 1 minus 2 sine theta, and that we're going to need to square and integrate that with respect to theta. And so we have quite a bit, but I still need to figure out what interval somehow corresponds to this inner loop. And so that's where we actually need the picture to figure out when are we actually on this inner loop thing. So let's go ahead and transfer over and look at my Desmos graph. Again, you have the link to get us here. And you can see that I've plotted our curve, and then I have kind of these different a values. So when a equals 0, this is basically taking the place of theta, or my angle. And so when my angle is 0, well, we point off in this positive x direction, and we get out the value of 1. And of course, you can double check that if you plug in 0 everywhere we see a theta, you indeed get 1. And so as you start to increase our angle here, we can see, well, that yes, the angle increases in this, counterclockwise direction. And we seem to be going along this outer loop at this point, right? So maybe this isn't a part that we really care about. But then after this point right here, we start to actually go along this inner loop. So this is the point that we're maybe most interested about. Kind of sometime here when we actually go through this origin, we start to now trace out this inner loop. And this is the bit that we're actually trying to figure out the area of. And then after so long, maybe about right here or so, we seem to go through the origin again, and then we're tracing out this outer loop all the way back to 2 pi, and that's where we would end. So, okay, I'm going to go ahead and maybe just hit the play button once and see this run through. So that's kind of the trace that we make. So in order to figure out the area of the inner loop, we need to know kind of what is this region or what is this interval in which we're actually tracing out that inner loop here. And so I need to figure out, well, when do we start and when do we stop? Because it's not at 0 and 2 pi, right? 0 here, we're tracing out the outer loop. And then after this point, again, we're tracing out the outer loop. So if I want inner loop information, I need to know when are we tracing out this inner loop. And so, okay, well, I need to figure out these maybe theta values here and here to tell me when do I start and when do I stop. And the big thing here is that they seem to be going through the origin, or that's when the radius is equal to 0. And so this is the main idea that I need in order to figure out what those theta values are. And so let's go ahead and set up some equations. Again, I want to know when is the radius equal to 0. And we can set up our equation. R equals 0, and again, we know R in this case is supposed to be our 1 minus 2 sine theta. And so I can go ahead and rearrange this, and I get 2 sine theta is equal to 1, or that sine theta is equal to 1/2. And so I need to know when is sine of theta equal to 1/2. And luckily there are some times on the unit circle when that happens. Right? So sine is supposed to be the y values on the unit circle. We know the maximum is 1 up here. And so here's some places where maybe the y value would be 1/2. And so this happens at 30 degrees, or that's going to be pi over 6. And then also over here at 5 pi over 6. So therefore theta is going to be either pi over 6 or 5 pi over 6. And let's just go ahead and double check that with our graph here. So if I plug in, right, because we can just type in here, pi divided by 6, we can see that, yeah, it seems to actually be going through the origin at this time. Or if I type in 5 pi over 6, again, it seems to be going through the origin at this time. So yes, I want to integrate from pi over 6 all the way up to 5 pi over 6. And that's going to give us our area. So again, by playing with this graph, we know that we should start integrating at pi over 6, and we should stop integrating at 5 pi over 6. This is when we trace out that inner loop, and again, we're trying to figure out the area of just this inside loop there. So okay, with that, now let's go ahead and do the calculus bit of actually integrating this. So to do that, the first thing we're going to do is expand, right, the squaring piece. And so I need to FOIL this all out. I think we're going to get 1 and minus 4 sine theta and plus 4 sine squared theta. And we're integrating that with respect to theta. Why don't I go ahead and factor out this 1/2 from all of these pieces. I'll bring that out in front of my integral here. And let's see, I'm not going to have any problem integrating 1. I'm not going to have any problem integrating 4 sine theta. But in order to evaluate out sine squared, remember this is again one place where we need to use the power reduction rule. And so let's go ahead and bring this up again over here, right? Sine squared u is going to be equal to 1 minus cosine of 2u, all divided by 2. And so we're going to use that in order to evaluate this. And so this is going to become, instead of sine squared, I'm going to write 1 minus cosine of 2. And in this case, my u is just my theta, so it's going to be 2 theta divided by 2. And let's see, okay, I've multiplied that by 4, good. And I need to integrate this with respect to theta. All right, now I've done kind of all of the algebra and trig work. Now I'm actually ready to do the calculus and integrate. And so let's go ahead and actually do the integral here. So when I integrate 1, I'm going to have theta. Again, I'm integrating or taking the antiderivative with respect to theta. Let's see, when I integrate negative 4 sine, I believe this is going to become positive 4 cosine. Double check, if I take the derivative, I should get back to where I started. And let's see, there's going to be a little bit of cancellation here, right? So this 4 and this 2, I could just make this 2 and distribute this to each piece. And so when I integrate 2, I'm going to get 2 theta. And when I integrate, let's see, 2 cosine, let's see, there's a negative here, I'm going to get 2 sine. And again, I have 2 theta in here, which that means, I've probably screwed something up, right? Because if I take the derivative of this, the chain rule would say I need this extra 2 to come out. So let's go ahead and multiply this by 1/2. Now double check, if I take the derivative of this, I should get back to where I started. Or you may have just said, well, let's go ahead and cancel out the 1/2 and the 2, and that's also perfectly fine. So again, double check, if I take the derivative of this, I should get back to where I started. All right, and again, we need to evaluate this from pi over 6 to 5 pi over 6. So now I've done the majority of the calculus work. I guess I could go ahead and combine together, right? We have a theta and we have a 2 theta, so this become 3 theta. And so let's go ahead and evaluate when I plug in 5 pi over 6 and pi over 6. And I'm just going to go ahead and highlight just so I know which pieces I've taken care of. And so again, I'm going to take care of the 3 theta first. So if I plug in 5 pi over 6 into theta, well, that's just 5 pi over 6. And if I plug in pi over 6 into theta, again, just pi over 6. Next up, let's go ahead and take care of the 4 cosine theta. And so let's see, there's a leading 4 here. And if I plug in 5 pi over 6 into cosine, so let me draw my little unit circle here. So 5 pi over 6, that's going to be negative root 3 over 2. And then when I plug in pi over 6 over here, that's going to be positive root 3 over 2. All right, so that's me taking care of the cosine. And then finally, I need to take care of the sine. So let's deal with that. And these ones we have to multiply by 2 apparently. So this is going to be sine of, let's see, 5 pi over 3. So let me go back to my unit circle. Here's 1 pi over 3. Here's 2 pi over 3. 3 pi over 3. 4 pi over 3. 5 pi over 3. So this is going to be negative root 3 over 2. So negative root 3 over 2. And then I need to subtract away when I plug in pi over 6. But again, we're multiplying this by 2, so it's going to be pi over 3. So that's going to be up here. And so this is going to be positive root 3 over 2, but notice that we're subtracting it away. All right, all this being multiplied by a half out front here. So let's see, this is 3, and let's see, 5 pi over 6 minus a pi over 6, so this is going to be 4 pi over 6. And I see there's going to be a little bit more cancel. Oh my goodness, words. Cancellation. Again, I was thinking cancellation. I was adding syllables. Cancellation. All right. So a little bit more cancellation here. And let's see. And we have even more there. So this 2 is going to cancel out with the 4, and we're just going to have 2 pi. That's quite nice. All right. How about moving on? We're going to have 4. And then let's see, we have 2 of these exactly the same, both being subtracted away from each other. So we're going to have minus 2 of these root 3 over 2's. And again, we get some cancellation. There we go. Haha. And then let's see, minus, and let's see, again, we have 2 of these things. So minus 2 root 3 over 2's. Whenever I mess up, I can just blame the cats. There we go. And so let's see what we have here. Close parentheses. We have 1/2, and we have 2 pi right here. This is going to be, let's see, with that negative sign, we have minus 4 root 3's. And then here we have minus a negative, so plus a root 3. And so let's see, we're going to have 1/2 times 2 pi. And again, you could distribute that through and cancel out if you'd like a little bit. And then this is going to be minus 3 root 3's. So this right here would be the final answer. Again, that would be the area of that inside loop there. Of course, looking at this, right, maybe it's not inherently obvious if this is a reasonable answer or not. And so since this is one that, again, we're still kind of getting used to the formula and everything, let's go back to Desmos really quick. And I've plotted, or I've written in our answer, 1/2 times 2 pi minus 3 root 3. And notice we get a little bit more than a half, right? So this is 0.54. So one thing that we should mention is that it's definitely good that this is positive, right? This is an area, not a net area or anything like this. So we should definitely have a positive answer. So I like that. And then when I look at this right here, notice that this is a 1/1 square. Maybe I can go ahead and color in the 1/1 square. There we go. So I've colored in this 1/1 square, and of course it should have an area of 1, right? Length times width. And so I need to look at this kind of area of this inner circle right here, or this inner loop, and I'd say that, yeah, that seems like it's about reasonable to be a half of that, right? Because again, our area came out to about 0.54 and change. So yes, this seems like a completely reasonable answer when I go back and I actually look at the graph. All right, so we got one more problem to cover to finish up this video. That is finding the area inside of one petal of, silly typo, r equals 2 cosine of 2 theta. So that's this 4-leaf rose as it's known, and we'd like to figure out the area inside of one of the petals. So again, please go ahead and pause this video and see how far you can get. Try to set up the integral that would represent the area. Again, you have to think about what interval should you be integrating over. And again, get as far as you can, and then we'll go ahead and go over the results together. All right, so I'll show you how far I got, and then I think, well, I still have quite a bit of work to do. Um, but in this one, right, I went ahead and I set up our equation, 1/2 r squared. So I took our r, I squared it, simplified a little bit, right, squaring 2, squaring cosine, simplifying with the 1/2, and so I got to here. And then, right, there's still a couple of things, right? How do I integrate cosine squared? And so very similar to on our last problem, there was a power reduction rule for sine. And so I need to use the power reduction rule for cosine in order to make progress here. And so let me go ahead and just write it down. That is cosine squared of u is equal to 1 plus cosine of 2u all over 2. And so that's what I'm going to need in order to make progress here. And then the other thing is that I need to figure out what are my bounds of integration, right? When should I be actually adding up this area or integrating in order to find this area in the one petal? And so looking at this picture here, if I was just guessing, I would say if I integrated from negative pi over 4 to pi over 4, that seems to be where this petal is, right? This seems, again, for our radiuses, we're starting at the origin and we're going outwards, and this seems to be where this petal exists, and that we'd actually be hitting it as if we were kind of doing rays out of the origin on this interval from negative pi over 4 to pi over 4. But that's just a guess, right? I'd like to maybe verify this with a little bit of math. And so the way that we're going to do this is we see that kind of the start and the end of the petal happen at the origin at radius 0. So again, very similar to our last problem, I'm going to go ahead and set up r equals 0. And remember, r is supposed to be this 2 cosine of 2 theta. And I'm going to try to solve this, right? What theta values would make this true? And so we could go ahead and divide by 2, and I'd get 0 is equal to cosine of 2 theta. And then maybe temporarily, it's a good idea to maybe set 2 theta equal to u, and just think about when is cosine of u equal to 0? Well, I know cosine of u is equal to 0, for instance, at pi over 2. That's a place that I could plug in to cosine and get out 0. Or also maybe like negative pi over 2. So negative pi over 2, that would be another one. Also 3 pi over 2 or 5 pi over 2 or stuff like this, but those are getting rather large angles. I'd like to maybe stick around, again, kind of maybe from negative pi over 4 to pi over 4 is my guess. So maybe these are more useful for me in this case. So those are my u values, but if I want to know what my theta values are, right, u is supposed to be 2 theta. So negative pi over 2, and so I can solve for that, and that's going to give me theta equals indeed negative pi over 4. And if I set u, again, 2 theta equal to positive pi over 2, this is going to give me theta equals positive pi over 4. So indeed, my hunch of negative pi over 4 to pi over 4 is correct, but this is kind of all of the algebra that goes behind showing that this is the case. I'm going to go ahead and cheat using a bit of technology and just kind of move this over. And so, okay, let's combine these two things. The first, that I know actually my interval here from negative pi over 4 to positive pi over 4. And then the second thing, I can go ahead and transform. Instead of cosine squared, I'm going to go ahead and use this power reduction rule here and write 1 plus cosine of 2u. Well, remember, my u in this case is 2 theta, so it's 2 theta, or that's the same thing as 4 theta, divided by 2. So a nice bit of cancellation here. And now we can integrate this with respect to theta. And so I'm going to have, let's see, when I integrate 1, I'm going to have a theta. And when I integrate cosine, I'm going to have a sine. And, oh, but this isn't just sine of theta, it's sine of 4 theta. So I think I need like a 1/4 here. Double check. If I take the derivative of this, do I get back to where I started? Yes, right? Because the chain rule, I need to multiply by 4, so that 1/4 will cancel it nicely. Good. And so let's see, we have negative pi over 4 to pi over 4. And so when I plug these things in, for theta, for instance, I'm going to have pi over 4, and I'm going to subtract away negative pi over 4, so that's going to be plus pi over 4. And when I do that for 1/4 sine, let's see, 4 theta, and again, my theta is going to be pi over 4, so that's just going to be sine of pi, which is going to be 0. And then minus sine of negative pi, which is also 0. So this bit just goes away, And it looks like my final answer here is pi over 2 for the area of one of these rose petals. And so just as before, let's maybe think about if that's reasonable or not. No, pi is around 3.14, and so this is approximately 1.57. And if I go over here and I just kind of look at this, well, let's see. Here would be a rectangle with area of 2. Or thereabouts, yes. So that would have an area of 2. And so, yes, this seems like it's less than that. 1.57, right? It's not terribly less than that. So, yeah, this seems reasonable, right? Pi over 2 seems like a good answer to me. All right, so that was our last problem. These were some nice-ish area problems. Of course, we went over some other ones in the videos, and we'll go over more in Monday's class when we return from Thanksgiving break. Thanks so much for watching, guys. I hope you have a wonderful break. I'll see you next week.